Okay, this video is about work. We have in class been talking about energy and energy's ability to do work. So today we're going to turn our conversation to what work is. And these are just basic definitions. And in class through our labs, we're going to understand how work in living systems plays out, how living things carry out work, how living systems carry out work. Some of them are pretty obvious when we talk about what we do, physically moving objects, but some of them aren't so obvious, like plants and some other objects in nature and living systems that we're not quite so familiar with. So, basics out of the way, and then in class through our labs, through our geotropism, our phototropism, our Turgor pressure labs, we're going to see these things as they work in nature. So, hope you have your notes. If you did not get them from class, you can print them out. I shared them through my Google Docs. You just print it. Even if you don't have a printer at home, it's just 7 questions. So you can write the 7 questions out, press pause as we come to one of them, write your answer in, and you're going to turn that in class for a grade. I'll give it back to you. It'll go in your journal and as a study aid for your test over this material. All right, so we're going to start with a definition of work. Work is a force acting through a distance. Hang with me. I'm going to hopefully explain this, and you'll have a better understanding at the end of this video and at the end of the next video. But you don't have work if you don't have force and distance. You've got to have them both there together. You're not going to have work. We're going to do some practice questions in class where there's no distance, and then so there's no work. So, distance is measured in meters. You've learned that since you were in elementary school. We use kilometers and millimeters and centimeters. So distance is measured in meters. Force is measured in newtons. Okay. So since we know that work is a force acting through distance, we have to put the newtons and the meters together. So when we measure work, how much work is actually being done, we use a unit of measurement called a Newton meter. You may have never heard of that before, and you might not hear of it again for a while. But for our class purposes, the Newton meter measures work. We have a formula for work that's very important. It's going to be on your formula chart. On the STAR test, it's in your formula chart in your assignment notebook. It's just one of those constants that we work with in science class. We're going to practice this. And so you'll be able to calculate some Newton meters in class. But we use the formula work is equal to force times distance. And here, this is what it looks like with just the letters. W is equal to F times D. Okay? So 1 Newton meter is equal to 1 joule. On our vocabulary last time for the quiz that we took last week, you wrote down the word joule. And you know that a joule is a unit of energy. Okay, so 1 Newton meter is equal to 1 joule. So, and then there's our definition again. A joule is a unit of energy. So make sure you push pause because I think I've answered some of the questions on your notes sheet. Make sure you have your answers and when you're ready to come on back, and we'll keep going. All right. So it tells us that work is the transfer of energy. We learned about potential and kinetic energy last year in other science classes. So potential energy is that stored energy, and kinetic energy is the energy of motion. So when we just talked about force and motion to have work, you've got the force to change from potential energy to kinetic. And that's important. And we'll give some examples of that in class when we do our labs and our activities. Okay, so in order for work to be done, there must be some kind of movement. Here's a little sketch that you might want to make in your journal or on the back side of your note sheet, just kind of somewhere in the empty space. Okay, so we've got a force that is represented by our arrow here. We've got an object, maybe a box or who knows, a book, maybe a house. And the force is acting on it, and the dashed line shows us that it's moving. Okay, the movement is going to be in the direction of the force. Lifting the trash can is an example of this. When you lift the trash can to carry it out, you could actually measure that. You're using a force to cover a distance. You can measure how much force you had to use with your muscles to lift the trash can. And then you can measure the distance. How high did you lift it up off the ground to get it out the door? you know that when you carry out the trash, sometimes you don't have to use a whole lot of force. Sometimes you do. Sometimes you have to use a lot more force. And so you can measure that and how much work is being done. Some smaller people have to lift the trash bag up just a little bit higher. And some people who are taller don't. We're going to talk about mechanical advantage in simple machines later. But that also helps us understand that this is something that's measurable. You've got force, you've got some distance, and we could actually measure that. But in my blue cloud right here, I also wrote that we cannot forget about gravity. Gravity is one of those forces that we've learned about for a long time. It's been around as long as we have, or we've let me rephrase that. We have experienced it as long as we've been alive, but we're not quite sure about it just yet. So don't forget about gravity and what it does. And we'll talk about that with our plants in just a second. So make sure you push pause, and if you have any answers that need to be recorded, you do so. Come back, maybe make a sketch, and we'll continue. Okay. All right. So my first blue statement says there's a force that's resisting you when you try to lift that trash can. Working with that example, there's a force that's resisting you. Okay, so gravity is that force. It's that resistance force. It's pulling us down. In class, I always talk about, well, where is gravity? Well, if you look at your feet, that's where the force is pulling us to. Okay, in class, I want you to transfer this concept to what we're doing in class with the beans and the corn and the geotropism. So think about our beans and corn, the geotropism and the phototropism. Those are both examples of how plants use force and resist force. Those plants had to force their way out of the cotyledon down to the soil. They work with gravity. They have to force their way through the soil. In our activity, we're using beans and paper towels. But still, they're forcing their way out. They're working with the resistance force of gravity. But for the phototropism, they have to work against gravity. They have to pull up against grow against the resistance force of gravity towards the sun so they can carry out photosynthesis. We talked about how those beans don't necessarily need the sunlight right away. They're down in the soil. But those little embryonic leaves, as they're pushing up towards the sun, they have to have a great amount of force to travel that distance. They're doing work so that they can get out above the soil, start turning green, carrying out that photosynthesis. So those are just some examples of forces in living systems that we've seen in just a few short days in our classroom. I know that's a question on your 7-question sheet, so make sure you push pause and get that written down. There's another definition here that we've written down, just another way of using it is input force is the force needed to do the work. If the trash can is really heavy, you need a greater input force. If it's light, you don't need as much. Those are just some examples. So push pause, write down your answers, and when you're done, come on back, and I think we're almost finished with this one. Oh, one of the things I know you've talked about before in science classes that we're not necessarily going to talk much about in our class. You will see some of these questions on tests. There's a simple machines question. So simple machines, just kind of remember from science classes past. What they do is they reduce the amount of force needed, or they make work easier for us. And I've drawn some, given you some examples of situation A, B, and then C. When you see these sketches and when you see these on tests, you need to understand what everything is showing you. So in situation A, we've got an arrow to indicate movement. Okay, so when the movement is straight up. So we're lifting this box, this 100-pound box, from the ground to the top of this platform. Okay, and the direction of the arrow shows you that it's straight up. Okay, so we know we have movement, we know we have force, we know we have work being done. Okay, in situation B, we have the same box, the same height, but instead of lifting the box straight up, we have an inclined plane. Okay, and so less work is being done, but the work is still, it's a greater distance, so it spreads the force out over a greater distance. And then in situation C, there's no arrows, there's no work being done here. And so if that was a question on a test, you would have to say, no, there's no work being done in that situation. So you may want to sketch these two somewhere in your journal and push pause if you need, rewind and go back. Always ask questions in class. You can either message me right away on Edmodo or write them down in your journal and ask me when we get back to class.